discussion from yesterday. First about the Riemann surfaces, and let's do the clearing up. Okay, so let's start again. Suppose I've got a manifold which is made up of a union of many patches. Okay, so there's patch 1, there's patch 2, there's patch 3, and okay. Now what I've done is this. You know, I've started with the manifold in which I had a metric, and I used the fact that on any given patch I can always go to a coordinate system where the metric takes the form ds squared is equal to e to the power phi dzi dzi bar. Well, let's call this phi I. This I use. Now, of course, I may not always be able to do this globally, because if I try to do this globally, then phi may blow up or blow down or something like that, like we tried on the sphere, right? On the sphere, we could always use the stereographic projection to project the sphere to the plane, and therefore you can always write the sphere as ds squared in this form, but on the north pole corresponding to the point at infinity, you have trouble. Something bad happens to this. This map essentially coming from the fact that you're trying to represent a compact space on a non-compact sheet. Okay, so a lot of infinity must squeeze to one point, and that's going to make this conformal factor behave funny. Fine. That's why we want to do this thing patchwise, because we want to avoid singularities of this phi function. Okay, so we've got this picture in mind. On each patch, what we've got is a dzi times dzi bar. Now, we've got some coordinate change between patches 1 and 2. So, x mu in coordinate 1 is some f12 of the coordinate in patch 2. Okay, that's what gives the whole thing a manifold. However, we know that this coordinate change is of the form so that after we make the coordinate change, the metric on overlap regions is the same viewed either from one or the other. I take the metric in patch 2, coordinate change it to patch 1, I should get back the metric of patch 1. In particular, the metric in patch 1 is of the dz1 dz1 bar form. The metric in patch 2 is of the dz2 dz2 bar form. Okay? So that means that if I take dz1 dz2 and I make the coordinate change, sorry, dz1 dz1 bar, and I make the coordinate change, I should get back to dz2 dz2 bar. Now, this is a mathematical problem we've encountered before in the study of conformal transformations. Right? Because the same problem of.
But in these transformations, you should ignore this infinities or that. Some part cannot be described by.
But that's why I'm using patches.
But in the transformation rules.
In the transformation rules, I will only involve them on overlaps between patches.
Oh, okay.
So suppose we were doing the sphere. My patch 1 will be everything other than the north pole. Patch 2 will be everything other than the south pole. On this overlap between the patches, the transformation's well behaved. That's why we're doing the patches. Okay? But let us remember that for the purposes under consideration, I want to patch up. I mean, my rule is that I'm going to patch up so that I always have dz bar in every patch. Okay, so the coordinate change going from 1 to 2 has to be the kind of coordinate change that takes dz1 bar to dz2 dz2 bar. But what kind of coordinate changes are these? I mean, takes this to something proportional to. Conformal coordinate changes, which means either completely analytic or completely anti-analytic coordinate changes. You know, we're going to preserve orientation, so we'll stick at the moment to completely analytic changes. Okay, so while in general, while defining a manifold, you allow arbitrary functions from one to the other, in our current context, we will only allow our functions, the z's to be holomorphic functions of z1s to be holomorphic functions of the z2s. Okay, so these functions that in which this would be the general structure of a manifold. In the particular case, we'll have z1 is equal to f12 of z2, and this is going to be holomorphic. Okay? So what this gives us here is the structure of a complex manifold.
Complex manifold, that's what you want.
Yes. Okay? And that, the requirement that we got from physics forces us to the structure of a complex manifold, where the coordinates on one patch are the holomorphic coordinates on one patch are holomorphic functions of the holomorphic variables of the other patch. So it makes sense to say what it means for a function to be holomorphic, for instance. Because it doesn't matter whether it's holomorphic in Z1 or holomorphic in Z2, it's an invariant notion. Okay? So this is the basic setting for the structure. Okay. Now, the various different ways, these various moduli of our manifold, okay, are going to be encoded in these holomorphic functions. And it's this structure of what happens as you come around that's going to be important. Because any one thing can always be undone by you can always, by making a Z2 a holomorphic function of Z2, you can undo one thing here, but you may not be able to undo the relative things as you go around. Okay? So these, the moduli, one way of thinking of the moduli are the set of inequivalent structure functions, these transformation functions. And inequivalent means what? Inequivalent means that, for instance, that you cannot get from one to the other by diffeomorphism plus while. That's how we started thinking about it. And we'll give actually a mathematical characterization of that inequivalent in just a moment. This is from this structure of these differentials we'll build up. Okay? So it's in this language. The purpose of the discussion is to recast the integral over moduli into integrals, so you can put the moduli inside the parameters in the transition functions between Z1 and Z2. So suppose I tell you that I've got transition functions between Z1 and Z2. I've got these patches and I've got my transition functions. This, up to a Weil transformation, completely characterizes my metric. Right? Because it tells me that the metric here is dz1 bar times some finite Weil factor. The metric here is dz2 bar times some finite Weil factor. So up to regular Weil transformations, it gives me the metric everywhere. Okay? So if I give you these patches and the transition functions up to well-defined Weil transformations, unto non-singular Weil transformations, I've completely characterized the metric everywhere. Okay? So the data of metrics modulo Weil transformations is the data of this patching, the patching of the patches and in the transition functions. So there should be a way of parameterizing the moduli by parameterizing, for instance, the transition functions. So let's say I keep the patching structure constant. I cover the manifold with 10 patches. And then I vary the transition functions. Okay? That should be one way of characterizing the moduli of my fields. And I want to give you a formula for the string scattering amplitude where we think of the moduli as moduli for transition functions rather than moduli for Weil and diffeomorphism in inequivalent functions, metrics. Okay? This is the goal of this exercise. You will see that there's a certain elegantness about it. It's also actually how people often work. This is the reason why I want to do this. Okay? Now, so
anytime you have a diffeomorphism on a manifold, any sort of diffeomorphism, you can map, you can take it to a mapping in the tangent space of the manifold.
An infinitesimal diffeomorphism is labeled by a tangent space vector. That's what you're saying?
You have if you have a diffeomorphism of the manifold is a map from the manifold to the manifold.
Yes.
So you can take this map and then you can act it on the vectors by, let's say, pull back.
You can take vectors to vectors. Yes.
Always take this mapping
Uh-huh.
and define an well-defined action on the tangent space, tangent vectors.
Sure. That's I think you're giving us the vector transformation rules. Yes. Okay. Yes. Yes. Go on.
I didn't want to say mathematics. I'm trying my best not to say.
Yes.
I don't say these things. But I don't say. But I want to know what you just said about transition functions. This is a classification. So you should have a statement about vectors, right?
Well, where are the
vector spaces? It's a classification of these transformation properties of the vectors.
Why vectors?
Because any times you give this function, these mappings, these transition functions, they are basically mappings from the one point on the manifold to the. You're just giving maps, right, from the manifold to the manifold. So you can as well talk about maps for the vectors.
But why should I talk about vectors? I mean, why? Why not 3 tensors? So, I mean, what is special about vectors?
It's good to. I will feel more comfortable if you tell me.
I don't even know what you're after. Let's see. So I mean, when you talk about normal, when you talk about a normal manifold, once again you have patches and you've got transition functions. What is the analog of what you're after in that situation?
Normal manifold.
Any differentiable manifold is defined by this structure. I mean, not necessarily a complex manifold.
Okay.
So forgetting about all these fancy structures.
Yes.
You always talk about these coordinate patches and the overlaps and transition functions. What in that context, what are you after?
Let's say if you have a finite dimensional differentiable manifold.
Yes.
Then you have a tangent space of dimension n.
Yes.
So once you give me this transformation rule,
Yes.
then that defines on a particular point, it's a rotation of these vectors.
Rotation.
At a particular point, it's a particular linear transformation on the vector space.
You know, there's the manifold. A point is a point. There's just one vector space associated with that point.
Yes. At every point, you have a vector space associated with it. Once you give this map, this is a map from every point to another point.
Okay, fine.
Every point,
Fine.
there is a tangent space.
I see. Yes.
Every point, it defines a transformation.
Yes. Yes. I agree. So there's a point in one neighborhood of Rn, another point in another neighborhood of Rn, and you map in particular the tangent vectors around this point to the tangent vectors around that point. This I agree with.
Mappings of tangent vectors.
Yes.
Tangent vectors.
Yes.
Okay. Now, depending on this transformation of these vector spaces, people talk about these complex structures. You know.
Okay.
So my main question, I'll tell you the question. I don't want.
Yes. Yes.
The question is it the same classification of complex structures, or is it something else? The classification.
It's just the usual, the inequivalent ways of defining a complex function when a function is analytic on a manifold.
So is it going to be the same?
What people normally talk about complex structures. When people talk about complex structures on a manifold, this is it.
This is it. So
This is it. Same thing.
Okay. That's all right. So then I can.
Yes. It's yes. Yeah. I mean, it's just giving a notion of when a function is holomorphic. Yeah. So it's holomorphic. It's holomorphic in any z coordinate, and it's a consistent thing because the z's are holomorphic functions of each other where they overlap. Just. Yeah. That's basically one way of thinking of it. Okay. Great. Fine. So now, what do we want to do? I want to take our old rule, which was this integral of this b del g. Okay, I want to take this object here and transform it, that quantity, and transform it into a structure that that is worded in terms of transition functions. Okay, this is my goal. Okay, so let's see. So first let me do the auxiliary calculation that I was trying to do yesterday, and we'll see how it fits into my goal. Okay, but the calculation I'm going to do is the following. Suppose on any one of these patches I do a diffeomorphism. Okay, suppose on any one of these patches I do a diffeomorphism. In order for this structure to be maintained, I'm going to have to do possibly going to have to do compensating diffeomorphisms on the other patches. But I will do them one by one. Okay? And my diffeomorphism is simply, I'll do it in vector notation first, and then we will transform to this complex notation. It's simply x mu goes to x mu plus V, I'll use his notation. I suppose it's V mu k of x mu. Delta tk, yes. I'll just check this is the notation. Fine. And he puts another index saying on which patch we're doing it. We'll put that later. Okay, we're dealing with the mth patch, so he has xm mu. It's a bit cumbersome. I may sometimes omit the m when it's clear. Okay, great. Now, the first question we're going to ask ourselves is how does the metric transform under such a coordinate change? We know very well. Okay, yeah, we know very well. It transforms, so we have e to the power 2 phi dx mu. Because we had a flat space times e to the power phi. Okay, and it transforms by just plugging this dx mu in here. Okay, so it's the familiar formula, right? The change of the metric is e to the power this plus okay, so let's look at the transformation of this. Plus there will be a part that just transforms the x dependence in here, which we will not care about because it's some overall Weil factor. Okay, we keep track of it, but it will matter not at all to us. Okay, so this will be just plus, so it'll basically, let me say, the change in the metric, delta g mu nu is equal to del mu v nu plus del nu v mu. Right? Where v is this delta. Let's call this whole thing v. Okay, and I'm omitting the m index. Okay, so that's the change in g mu nu. There will also be a change from the phi, which we don't care about because it only transforms the overall Weil factor. Okay, and now we specialize to the case. We specialize to the case where we're in 2 dimensions and we've got a single z coordinate. Okay, so we will get delta gzz is equal to del z vz. And maybe 2, okay, 2, we'll drop the 2, and delta gz bar z bar will be del z bar vz bar. This is clear, right? And there will be a delta gz z bar, which will be del z vz bar plus del z bar vz, which we again will not care about because it only transforms the overall Weil factor. We are only interested in the part that cannot be absorbed in overall Weil rescaling. Okay.
You wanted these things to be holomorphic, so I think that'll be easy.
What? No, I didn't. This change I don't want to be holomorphic. We must be careful.
The notation up there, right? You have your v is just a function of x mu.
X mu was both z and z bar.
Oh, okay. So in your formula, right? That sort of x mu is like it makes me think of the project.
I'm sorry. V mu vz is equal to vz of z bar. Vz bar is equal to vz bar of z bar. Okay. This is not holomorphic. What must be in the end is that once we do this change in every patch, the transition functions remain holomorphic. We can involve some non-holomorphicity here, some compensating non-holomorphicity here, such that the transition function remains holomorphic. That's all we care about. Okay, this need not be holomorphic. And in fact, you'll see in a moment that that's a crucial point. That anything that can be absorbed in holomorphic coordinate changes, patch by patch, never gives us anything. It's only such that in each patch you do a coordinate change that is non-holomorphic, but that results in a compensation so that you get a holomorphic transition function still. That gives you something non-trivial.
Anything you can break without messing up the transition functions being well defined.
Yeah, you see, if you do a holomorphic change coordinate by coordinate, you haven't changed the manifold at all as a complex manifold. You've just renamed your coordinates. So that's the trivial thing. We want to get new complex manifolds. Okay? Yeah. So, so let's keep going. So this was our structure, and we will, following Polchinski, we'll use upper indices. So this will be z bar, and this will be z. We're using z and z bar mix under raising and lowering. Okay, very good. Now what are we interested in? We are interested in evaluating our old formula, that's this B del G, on such changes of the metric. What I'm going to do is going to do such coordinate changes patch by patch and do it over the whole manifold and evaluate this quantity on the whole manifold. Okay? That's my goal. So what I've got now here is a formula for what this del k G is. Because what I've done is, this thing that I'm doing is going to parameterize my modulus. So this small change is small change because of a change in the modulus. So it's the change in the metric because of the change in the modulus. Okay? Now this del kg of course also had a part due to the change in the Weil factor. But yesterday we checked that was 0, right? That contributed nothing to this, basically because B was traceless. That's why we're not keeping track of that from this point of view. Is this clear? Okay, so let's keep going. So what we want to do is to evaluate that. So the thing we had to evaluate was B mu nu del k G mu nu e to the square of G. Okay? Now, or we've checked previously that all the e to the power 5 factors cancel out in this. Anything that where the derivatives acts on the e to the 5 will cancel because of tracelessness, and anything else we've checked where homogeneity just goes away.
I'm saying something, you'll say if I'm saying that.
Go on.
Wrong reply.
Go on.
So, what I want to do is to integrate over all the matrices modulo this Weil factor.
Yeah.
This is what I want to do.
Yes.
And so I want to get all the complex manifolds modulo this Weil factor. And to see these are, if give me two manifolds, two complex manifolds, if all of them are related by holomorphic changes, then they are related by Weil factor, so I consider them same manifold and I don't integrate over the
Exactly.
manifold.
Exactly.
To get a different
Just, I think a mathematician would say, you just want to look at the set of inequivalent complex manifolds.
yes.
Because, all they're interested in is this complex structure, this notion of what it means to be holomorphic.
And the complex manifold came precisely because we cared about Weil equivalence.
Exactly. That's exactly right.
So Weil equivalent, therefore they are complex manifold.
See, because we cared only by Weil equivalence, patch by patch we made it dz bar.
While the gauging while means that we talk about different complex manifolds.
Exactly. So we want to sum over the inequivalent set of complex manifolds, basically. Okay. So now we moved from this Weil blah 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 to what mathematicians like, namely the moduli space of complex manifolds. Okay. And now I'm going to try to translate our physics formula into mathematicians' language. That's the goal. Clear? Great. So all those e to the power 5 factors cancel out, and this thing is just B, let's say z del k g z z plus the other part b z bar. In fact, we'll call it z bar g z bar plus the other part, because this is the holomorphic guy, because when you lower it becomes bzz and that's holomorphic. Okay, so we'll write this as integral bzz del k. So del k is now the small change. Now we just substitute. Okay, we want B z bar change in z bar, which was del z bar of Vz. Okay, so del z bar of Vz plus the other term. Clearly Vz is like C. I mean, in some formal structure, but firstly notice that if Vz here was completely holomorphic, this would just be 0. Those are the trivial things. Yeah, those are the things where you're not changing the complex manifold as a manifold at all. Okay, so only things that are non-trivial can give you something 0. But this question came up yesterday. The question was, in the end, all you're doing is a coordinate change. So surely it should just. So if we were doing it on the whole manifold, if there weren't all these patches, it was just one sphere, let's say, one. I don't know, there's no such thing, but if there was just one thing, then we could integrate by parts and we would get 0. Because B is holomorphic. Okay? But the whole point is that we can only do it in this patch. And integration by parts has a boundary term. Okay? This is the point. This is the crucial point. Okay? And so, what we get by integration by parts, we've got this patch, we get a contour around this patch, and by Stokes' theorem, integrating this by parts, there's a del z bar of Bz, z, Vz, and as we've seen before in the Stokes' theorem kind of arguments, this gives us dz of Bz, z, Vz.
Is that just the kth component of Bz?
What?
Is that just the kth component of Bz?
What is kth?
Well, it has.
Yes. Now, let's say I'm doing a particular modulus variation at the moment.
Okay.
I'm focusing on that one guy. Let's do it piece by piece and then we'll sum them up. Is this clear? So this factor that we were supposed to insert, when we do the change by doing it in this mathematician's way, by changing the complex structure, the part coming from my little patch, okay, gave me this quantity. What?
It's again looking like an insertion of an operator.
It's looking like an insertion of an operator, but it's interesting. It's an insertion of a contour. See, this was an integral. This was an integral over the whole manifold. Now we've turned it into a contour precisely because piecewise it's a diffeomorphism. So it can't be a bulk term, it could be a boundary term. Okay, now this is a bit strange by itself. In particular, it looks like if I wiggle the surface, I'll get a different answer. Because remember, Vz was not holomorphic. Right? Because if Vz was holomorphic, we get nothing. So it looks a bit strange by itself. But remember, we have to do the same thing for every patch. And we can't do it just with this patch. Because if we did, then if we take z goes to z plus something involving z bar, and now we asked for the map between this new coordinate and the old coordinate, it will no longer be holomorphic, which means that the metric dz in this space can't map to dz in the other patch. Okay? So we cannot do this just on one patch. This is a coordinated operation. It requires all battalions to fire simultaneously. Okay? Great. But this is what we've done on one patch. Now, the question I'm going to ask is, so suppose I do this now on the mth patch. Okay, so I get this quantity from the mth patch. I will also get a similar quantity. So suppose I have my contour here and I've got an overlap here. I get a similar quantity. Let's say I put my contour here on the nth patch. Yeah, maybe I should use two colors. I'll draw this. I've got my first patch that's here, my second patch that's here. I cover this much of the first patch. I have that integral which I have to do over the whole manifold. I break it up into integrals over various different patches. Okay?
Common lines from others.
Yeah, so this part of it I do with the other guy.
Every one of them is going to have common lines.
That's
Because you have to cover the whole manifold.
because you have to cover the whole manifold, exactly.
And only you need to calculate the differences.
But exactly, what you need to do is calculate the differences. Perfect. So let's see. So what we get here, as Indranil said, was this guy going this way, but this guy also going this way. And because one's going this way and the other's going this way, you need to calculate this quantity, BZZ, VZM minus the corresponding quantity in the other patch. Now, I want to give you an interpretation of what we're calculating. And that interpretation is very nice. It goes this way. See, suppose I had a function. So suppose this was in the mth manifold and this was in the nth manifold. Okay, where Zm was equal to some function of Zn. Now the transition function has changed. Okay, how do I characterize that? One way of characterizing it is the following. How much does Zm change if Zn is held fixed? I change my tk. Okay, so a characterization of the change of the transition function is del Zm by del tk. Del t, we're not keeping a k index. Del Zm by del t at fixed Zn. Okay, that characterizes, I mean, that's basically this. That would be, the change of how much this function has changed evaluated at the point Zn. Right, I'm not changing Zn, but I'm changing this function.
In this neighboring contour,
Yes.
blue one, red one,
Yes.
their functions on one contour is related with the other with this changed transition function.
I didn't understand. Say again.
The blue one is mth contour
Yes.
and red one is nth contour.
Yes.
Now functions on mth contour
Mm-hmm.
is related to functions on nth contour by the new transition function.
Now the new transition function is infinitesimally related to the old transition function.
Yes.
So this contour that we're writing down has no infinitesimals in it, right? It's some derivative. So this contour evaluates a quantity that knows about the change of the transition function, but all quantities are evaluated in the old transition functions. It's like this, right? We're taking the derivative of the metric but evaluating it on the original manifold. Right?
Yeah, because this is double order.
Yeah.
Double order.
Yeah. Exactly. Okay. So let's keep going. So this quantity is a characterization of how much the transition function has changed. If I know this, I know how much the transition function has changed. Okay? Now let's work out what this quantity is in terms of our v's. So what I've done is do the following. First I changed Zm. So Zm was equal to Zm plus Vm. Vz. Okay. On the other hand, I also changed Zn. Zn was equal to Zn plus Vm, Vn of Z. Now, I want to do the following. I want not to change Zn, but to see how much Zm changes. Okay? So I have to move to a different point. Okay? So what do I have to do? I have to work at, I want to see what Zm is if evaluated at the Zn. Okay, so evaluated at Zn. So now suppose I evaluate things at Zn is equal to Zn, the old Zn, minus delta Zn. So that my Zn doesn't change, minus this Vn Zn. Okay? Then I want to see how much this Zm has changed. So how much does that change? Well, clearly it's the change in Zm. Change in Zm is equal to how much it's changed because Zn has changed by this much. So del Zm by del Zn with a minus times Vnz plus Vmz. Okay? So this is our measure of the change in the transition function, this complicated looking quantity. But you know, this complicated looking quantity is actually quite simple. Because what is V? V is a vector field.
Oh, this is a differential from the side.
Yeah, V is a vector field, and this vector field, its components are referred to the coordinate Zn. So we move on the overlap, we can move the coordinates of this vector field to the coordinate.
So this differential is basically telling you what the linear map you have to do is to go to get the new metric from the old.
This differential, which differential?
Over here, this difference between the two.
This difference between the two? Well, it's the quantity that appears in here. Hang on for a minute, it's going to be...
It's just the same vector field written in the different coordinates.
Exactly. This was written in unnaturally because this vector field referred to the coordinate Zm. This vector field referred to the coordinate Zn. But this combination turns it back into the coordinate Zn. Okay? So this is delta Zm, this quantity, this thing that we are interested in, the thing that characterizes the change in the transition function. I'll call it del Zm by del T and Zn. This is equal to Vmz minus Vnz. So here we should have had Z, to be really precise, we should have said Zm here and Zn here. This is the vector field in the Zn component. And here it's Vmzm minus Vnzm. So, Indranil will be happy to note we're dealing with vector fields. These are the V's. And what we're doing is we've got a vector field here that is relevant to this coordinate transformation. A vector field here that's relevant to this coordinate transformation. Since it's a vector field on a manifold, in the overlap region, both vector fields can be referenced to the same coordinate system. Once you do that, it's natural to subtract them. Okay, until you do that, it makes no sense to subtract them. Okay, and what we get, the thing that characterizes the change in the change in Zm at fixed Zn. Okay, this quantity is this just the difference between the two vector fields? Sounds very reasonable, right? Now, each of these vector fields is not holomorphic. But if we've got a transition function, if we've got something that is going to get us back into the structure we want, then this difference had better be holomorphic. Okay? So now this is a much nicer structure. Because the thing that we're integrating, so we only want to integrate the differences. So the thing that we're integrating is integral of this quantity, del Zm by del T at Zm at Zn, which looks very non-symmetric between M and N. But you see that when you write it in the right way, it's just the difference between the two vector fields, so it doesn't matter which way, which order you put it. Okay, which is integral Vmz minus Vnz, and the crucial thing is that this thing is holomorphic. Because it's holomorphic now, you can move around the contours as you like. It doesn't matter how much of this you used here and how much you used here. You can move it around as you like. Now, when three guys meet,
This vector field is defined. This vector field Vm is defined on the patch, right?
on the overlap.
So.
Sorry, Vm is defined on the patch, Vn is defined on the other patch, and this difference is defined only on the overlap.
Do we imagine that Vm is not defined outside of M, or is it 0 outside of M?
No, it could blow up, for instance, outside of it.
So we can't.
You should be able to take it all the way.
Okay.
Otherwise, the whole patch business was not necessary. Okay? Great. Okay, so now we're in business. And this is the quantity that we're supposed to integrate.
Sorry, for this part of the argument, you don't need that B is a function of only J.
For,
B is anything.
for this part of the argument, we don't need B the ghost field, you see. Yes, but of course, in order to get the contour structure, we needed that. In the integration by parts, we need it.
Integration by parts, you use that.
Yes. Yes. Right?
Isn't there a factor of B in front?
Oh, there is a factor of B. I'm sorry. Yeah. This is what we said yesterday. You know, because of the equations of motion, change in diffeomorphism is total derivative. But we use the equations of motion. There is.
He just took this del Z bar outside and then integrated.
Exactly. Okay, good. So this is one way of wording the thing. That is, if you want to do your integral over manifolds, if you want to do your integral over moduli space by doing it as an integral over complex structures, what you're supposed to do is this: parameterize your complex manifolds by patches and transition functions, and get m moduli, m parameter set of such transition functions. Once you have the transition functions, compute this quantity. It's completely defined by the transition functions. Okay, that quantity is what goes in here. Integrate with B over contours, and that gives you your measure for the moduli space integration. Okay, is this clear? If so, I'm going to give you one application, but yeah.
Even if you have a triple overlap, at this point, you'll only ever have 2 lines meeting. So
You
you
know,
only have to deal with
but you might wonder whether, when you have a triple overlap, whether the point of meeting matters. You might wonder whether I can do this or move it, and the fact that this is V1 minus V2, this is V2 minus V3, and this is V3 minus V1 makes it not matter. Okay, so that's easy to check, because one.
It's not enough to say I'm removing the point of an integral, so it doesn't matter.
No, because you're not just moving the point, you're moving where the line ends.
I'm removing the point of an integral.
What?
I'm removing that one point out of my integral.
No, it's not just that. It's you see, you want to compare this to this.
Okay.
It's a serious issue, right? Okay, but the point is that you collapse two of these like this. What you're collapsing it to is V1 minus V3, because the V2s cancel in the middle. Yeah, just work it out. It's a very simple thing. Now, you can easily convince yourself that it doesn't matter, that this move doesn't matter, because the structure is difference of two terms. Okay.
So the only kind of functions for which this integration makes sense, this integration is well defined, is for some holomorphic different two forms. B is a holomorphic. You use that term, B is holomorphic.
I used it in my derivation, yes.
So only for those kind of functions, this kind of integrations make sense.
I don't know what makes sense. Certainly, we only need it for those kind of things. I mean, if that's what you're saying, I agree with. If you're saying something more structural, I don't know. Yeah, yeah. Okay. Now, is this clear? Yeah, I have to confess, when I first took a string theory course, I found this very confusing. Okay. Okay. I periodically still find it very confusing. but okay. Yeah, you just have to think through it carefully. Also, Pulchinski's written it badly, and non-Pulchinsky textbooks, oh God, forget it. Yeah, they go into some mathematical language. Okay, okay, yeah. So, yeah. But it's a very simple thing, as you see. You just have to keep your wits about you. Okay. Now I'm going to give you an application. One application is a way of writing the string scattering amplitude in a way that is more symmetric between points of insertion and the moduli of the manifold, the thing we were referring to in some rough discussion yesterday. Okay.
Sorry, before we move on, the statement that Vn minus Vn is homomorphic, that was a result or a constraint?
No, that was a necessity.
So if this is satisfied, then everything else, then we're done with this.
Yeah, and it had better be. Otherwise, we weren't making then these coordinate changes weren't preserving weren't giving you a complex manifold. Yes.
Patching.
Yes. That's what, right. So we have to do only those kind of coordinate changes that make that holomorphic.
It tells you how far you can bend it.
Exactly. Modulo those things that are holomorphic by themselves.
Right, because that was already.
That was trivial.
Yeah.
Okay? So it's these sets of vector fields such that differences are holomorphic modulo holomorphic individually characterize the set of complex structures on the manifold.
You're saying that when the vector field is defined, if the differences are holomorphic, that's the only case when it's well defined. Otherwise,
that's what when it's doing what we wanted to do.
This really does sound like a gauge story. Yeah. It's like.
saying because V didn't have any restriction, right? It was not holomorphic or anti-holomorphic.
V was not holomorphic, but you remember what we wanted was to change the transition functions, but keeping them holomorphic.
I know, but I'm saying that we didn't have any conditions. Then we know that the transition functions are holomorphic. Then we found that the transition function changes by this thing.
This thing?
Hence, this should be.
Should be holomorphic,
But,
exactly.
What ensures that it will be?
We're only going to look at those coordinate changes that keeps them. You see, because what we're doing is changing one complex manifold to another.
I see. Okay.
We're trying to do that, right? So we're doing it by coordinate changes, and if we don't get this, we've not achieved our goal.
So then sort of the statement that by looking at these kind of vector fields, we'll be able to get something like the space of these on the sphere is one-dimensional, the torus is
Yeah, exactly. First, you have to define your path structure, all of that.
But then it shouldn't matter, right?
Of course it doesn't. Of course. Once you've given your topology, yeah. Okay. Now, since we've gone through all of this, I'm going to give you one application. And this application is a way of making the string scattering amplitude look more symmetric between insertions and moduli of the manifold. So the way I'm going to word it is the following. Look, since we've fallen in love with these patches, we might as well do the following. Every time we've got a guy, every time we've got a vertex operator, I'm looking at the integrated vertex operators. Instead of thinking of an integration, which is something mathematicians don't like to do, you can think of it this way. You can think of a new patch associated with a puncture. So you can think of the Riemann surface without any puncture, without any insertion, and then characterize where that insertion is by giving the transition amplitudes between this patch associated with the puncture and the patches associated with the Riemann surface. Okay? there's a special patch associated with this puncture. And then I'm supposed to tell you how that overlaps with all the patches that define the manifold. Okay.
Transition functions would involve the information about
V is what?
V was the operator which you inserted.
No, so the transition function does not involve the information about V. Yeah, it just, you see, we take the patch and by convention we put V in the center of the patch. I will continue to insert the operator V.
Okay, so far you can always do that. Whenever you have an insertion, just make us
Little neighborhood, yes, exactly. Make a little neighborhood and say in this neighborhood V is always in the center, and I will encode where it is on the Riemann surface by giving transition functions.
where is an information specific to the operator encoded.
I will still insert the operator V at the center of this thing. You know, so I'm just adding a few more patches to define my surface, and on one of the patches V lives.
The other patches could intersect with the insertion.
Yeah, the other patches will intersect with the insertion, doesn't matter.
You can make it smaller.
You can make it smaller, you can make it bigger, nothing will matter.
Yes.
Yeah, okay, fine.
Instead of giving its coordinate, you are giving me the patch number.
I'm giving the patch number and how it intersects with the other patches. Yeah, you could open out a space if you want in your patches for 3 months, or you could just keep the old patches and let this be a new one. That's okay. Anything's up to you. Okay, fine. Now, in order to do the integration, inserting this at different points is changing the patching. You're changing the overlap functions, the transition functions, not of the manifold itself, but of the insertion points, of the insertion patch with all the others.
Now let's repeat the sentence.
Yeah, say I've got my manifold, and this manifold has some patches. What I want to do, what simple-minded physicists like me want to do, is integrate over this manifold. Okay, but what these guys will tell us we should do is to have a patch overlap. So first I want to characterize the difference between it being here and here. What that is that when it's here, this patch has certain overlaps with this patch. When it's here, it has overlaps with this patch. If it moves here, it still has overlaps with this patch, but different overlaps. So moving the operator is changing the transition functions involving the operator patch. Okay, so I'm going to characterize the position of the operator, the change in position of the operator, by another differential with respect to transition functions, this time associated with this transition patch. But of course, once we've got this, the mathematicians don't like to say this patch is associated with the operator and this patch. It's just a bunch of transition functions. Okay, great. Now, you remember that what I did was every time I had a transition function and a patch, I had to insert this. I had to insert this object. Okay. Now, let's say that I'm inside a particular patch. Okay, I'm inside this patch, Zi patch, and I want to put my operator at Zi equals Z. So this is a Zi patch on the manifold. I've got a patch, I've got the operator patch, where the operator is always at Zi equals 0. So we have Zi manifold is equal to Z operator plus A. Because that's how you will insert the operator at the point A. So now A is like our T, right? It's the modulus associated with the patching of this operator patch. Okay. So the thing that we are supposed to integrate here on this overlap between the operator patch and this patch is the change in the transition function because of the change in T, but which is A. So change in the transition function, change in Zm because of the change in A at fixed Z op. Okay, but that's equal to -1 del Zm by del z op, sorry, del A at fixed z op is equal to -1 or +1. Clear? And therefore, the thing that we're supposed to integrate around this patch, if we follow the old rules, the thing that we're supposed to integrate around this patch, if we follow the old rules, is integral b times that change in transition function business, so that's 1 around this, so just integral b around this patch. So associated with the operator patch, we should have integral dzb. Now, for the integrated vertex operators, we did not have an integral dzb. Okay? What we had was just v of z. Okay? But now you can ask, can I change that v of z and add in an integral b so that the final result won't change? So we didn't have an integral of b, and we didn't have an integral of b. But now see, what I'm claiming is the integral db, b db, so b dz, b of z, d of v of 0, c of 0 is equal to no integral v of 0.
Left hand side you integrated over z.
What?
Left hand side you integrated over z.
Yeah, contour integral.
Because 1 by z you are getting probability.
Exactly. It's just because the pole of this, C has no pole structure with V, C with B has a 1 by Z, and so that establishes it. And so, if I do this mathematician's trick and I associate the integral with the change of moduli associated with the puncture,
What I am understanding is that you have an honest integration over z, d to z, v of z.
yes,
This
that's
is
what we
an
want.
honest integration.
Yes.
I am rewriting d to z, vz as d to z, v, replacing vz by another integration of dz prime, bz prime, c0, v0.
Exactly.
Now the dependence is holomorphic in z prime, which was needed here.
Yes, yes.
Now I can rewrite one part of this integration as an integration over this moduli space, with this kind of transition functions.
Yes. I'm saying that
A part of it you can write something more.
everything. I mean, so this is just an identity, right?
You just multiplied it by 1.
What?
V of 0, you just multiplied it by 1. The v of 0 never showed up in the integral.
Exactly. V of 0 never showed up in the integral. All I've done is to show, is to use that integral b with a c is equal to 1.
Yeah.
That's all I've done. So I've just inserted this identity into the old story. But once I've inserted this identity into the old story, two good things happen. Firstly, all operators are associated with an insertion of CV, rather than some operators being associated with an operator of V and some with CV. But then you say, well, that's a fake, because you've associated this with an insertion of CV, but at the expense of putting a contour integral of B around here. Why would you do that? But you would do it if you thought in this language, because this language instructs you for every modulus to put the contour integral around B. Yeah. With the factor that works out exactly. Okay? So, there is a way of taking this formula and writing it in a way that the mathematician would like.
So at the end, are you concluding that this integration,
Yes?
you had an integration over vj d to z, right?
Yes?
Are you concluding that this whole integrated quantity is rewritten as an integration over moduli space
Yes.
up to some c0, cv at fixed point?
Right. So let me write down the final conclusion. More or less what you said, but let me write it down. What we had on the left hand side, the honest thing, was d2z vs. Okay, this is changed to integral over larger moduli space. Okay, and fixed v replaced by cv
At fixed point.
at a fixed point, and then the integration is taken because of the moduli space. Yes. Okay, ghost number continues to work because we added a c and we've added a b. Okay, in fact, from this point of view, we were supposed, from the point of view
Now you have also proved that it doesn't matter which point you fix by conformal killing vectors because you have fixed all the points.
no, okay, yeah, except that these moduli are associated with some punctures.
Okay, they are parsing.
Yeah. Okay, but this gives some purposes of a formally elegant formula for this integration over moduli. Okay, that's all I wanted to say about this. Any questions or comments before we move on? Okay, fine. So now what we have is a quite thorough understanding. Now what we have is a quite thorough understanding of the rules for computing the amplitudes for string theory. The rules for computing the amplitudes for string theory, the bosonic string, at least at first pass. What I haven't really told you about very much is how you should add together the contributions due to different manifolds. If you remember one of our early lectures, I said, well, the scattering amplitude should be on the sphere, plus on the torus, plus on homogeneous surfaces. That mimics this tree level, one loop, two loops of field theory. But you know, in field theory, we also have a coupling constant. Okay?
That may differ from manifold to manifold.
A coupling constant, exactly. That in fact, the way we work in field theory, it's just the number. A coupling constant appears like coupling constant to the power of to order of loop number. Okay. So, do we have something like that in string theory? Well, there is this obvious possibility that we haven't talked about. Okay, and that the obvious possibility is this: that when we were looking at our string Worldsheet Lagrangian, we were working with Polyakov actions. We were working with gravity, quantum gravity on the Worldsheet. But we didn't add any purely gravitational terms. We didn't add any purely gravitational. Hello? Huh? Today? I'll pick him up at 7:45. Okay, fine. Fine. Okay, I'm teaching, so I'll put down. Huh? Okay, yeah. Okay. Sorry. Coordination with my children's schedule is always tense. Okay. Okay, excellent. So, though we worked with the Polyakov action, we never wrote down Einstein action for gravity on the Worldsheet, and why not? Why weren't we for? Exactly. Because integral square root g violated conformal invariance. It's a cosmological constant type term. In fact, if you remember our first quantization of the string, we added a counter term of this sort to cancel the vacuum energy. Do you remember that's the thing that gave us 1 plus 2 plus 3 plus 4 was minus 1 by 2? You remember that, right? This was okay. We weren't allowed to add a free parameter like this. We had to add a fixed thing to maintain conformal. But this guy is scale invariant. d2x, two derivatives, scale invariant. Okay? Why can't we add this? Now, Indranil has given us the reason. The reason is that this quantity is a topological invariant. We've encountered this before. Okay? This quantity evaluates to, somebody knows the answer, 1 by 4 pi, doesn't matter very much, but what is it proportional? 2 minus 2g?
Yes.
2gg, okay, something like that. Okay. So because it's topological, it doesn't affect any local physics. But for the partition function, for the full partition function, if you added it, it will matter. Right? Because for the full partition function, when we sum over genus,
So sorry, I have written that everything.
go on.
You said that you take V at any diffeomorphism of this stuff, which is any diffeomorphism which does not change your metric only by Y transformation.
Yes, which changes your metric, which does not change your metric only by, yes, go on.
Only by diffeomorphism for which all this analysis.
Yes.
And in particular, now you need to tell me what are the different some basis, right? Did you tell me some basis or not
For the space of these diffeomorphisms.
for the space of this diffeomorphism?
Yeah, now that of course is the space, the basis is given, there's the number of parameters in such diffeomorphism. It's very important this is a coordinated move. You can't change in one patch without changing the other patches. Right? And anything that is purely holomorphic in any given patch is treated as trivial.
Yes.
Okay, or in all patches is treated as trivial. There has to be some non-holomorphic element. Okay, now the basis of course is a complicated thing, but the number of parameters in this thing will be the number of parameters in the moduli.
And that has some proof.
That has some proof. That, yeah, this,
All I know is this B0 modes is.
you see, so we
You prove one thing that if we take BC action and the number of zero modes per B,
yes,
that is equal to number of the directions, perpendicular directions, the number of moduli.
so you are asking, can we prove that the number of the parameters that parameterize metrics that are inequivalent up to while and diffeomorphisms is the same as the number of parameters parameterizing conformal manifolds, complex manifolds? That's the question. Yeah, this has some proof. It's almost clear. So you probably have to prove something, but it's almost clear. Because you see, suppose we are interested in looking at things suppose we are interested in looking at things in the while plus diffeomorphism way. Then we make these patches, like we said, we can always make these patches. Things only depend on the complex structure. Right? Anything that differs by that differs only on phi but has the same transition functions, same mappings, is equivalent. So it's clear that what is clear? It's clear that there is a well-defined map that all equivalence classes, while equivalence classes, suppose I want to map while equivalence classes to complex manifolds. It's clear that all while equivalence classes map to the same complex manifold.
Yes.
Okay. Now we want to prove that the reverse is also true. Okay, that that complex manifolds map to a unique while equivalence class. So what we want to do is to put a metric on complex manifolds in a way that is unique up to while equivalences. Now, there's some standard. Okay, this can be done. I know it uses the I know I've been through proof of this once, which uses the partitions of unity, whatever that happens to be. This is a standard mathematics proof. Okay, I won't try to reproduce it here, but it can be done. It's a standard thing. Okay.
But sorry, I have
Go on.
there's the connection. Now it told us
Yeah.
there are 4 complex structures: plus plus, plus minus, minus minus, minus plus.
No. That's that's not. There are 4 spin structures.
Sorry, it's 4 spin structures.
That's a totally different idea.
And this has nothing to do with this one.
No.
Okay.
On a torus, there's one complex parameter set of complex structures labeled by tau.
These are different.
Yes. Yeah. That's the number of inequivalent topological ways of putting spinners on the manifold.
Yes.
This is the number of inequivalent notions of when a manifold, when a function is holomorphic. Yeah. Okay. Okay. Right. So remember the thing that we were doing was this integral dB, dc, dx, blah blah blah, e to the power minus s, and we now suppose in s we put an alpha here. Okay. So this will pick up a factor of e to the power minus alpha by 4 pi, 2 minus 2g. Okay, let's call this whole factor e to the power minus, let's call this 1 by g closed square, 1 by g closed, some name. I'm just trading alpha for some name. So this is 1 by g closed to the power 2 minus 2g, which is equal to g closed to the power 2g minus 2. Now this is precisely the form in which a coupling constant appears in field theory.
Number of loops.
The number of loops, as you increase the number of loops, you increase the coupling constant by a fixed number. Each loop increases it by another factor of g square. And it's also very natural normalization because the classical action, namely g equals 0, comes with 1 over g square. Right? It's the way you would get factors of, in some normalization, it's the way you would get factors of coupling constant, just because the action has a 1 over g squared outside. Okay? So, this is certainly a freedom we have in string theory and we will use it. Okay? And roughly speaking, this G string, this GC will be a coupling constant, such that GC very small will ensure that the sphere dominates, that low loops dominate. GC very big goes to strong coupling, and you don't know, really, it's hard to, this perturbation theory we're talking about will become less useful. However, this GC is only part of the story. This GC is only part of the story because of the following. As I have tried to emphasize, but I will remind you again, the formula for the string scattering amplitude is given by the full path integral with operator insertions, not by path integral normalized with path integral with no insertions. In fact, the path integral normalized with no insertions doesn't even really make sense. Okay? So, what we are trying to do is to compute. Now, it's very easy in quantum field theory to compute, I mean, very easy, but we're very familiar with how to compute normalized path integrals. We're very familiar with how to compute correlation functions.
But if GC is not very coordinated some number, say some random, then the ratio between one loop and two loops, the 0 loop and 1 loop is becoming different depending on if you change GC. And then usually when you give the proofs of unitarity, these things can, like one thing square is equivalent to other thing not squared. Let's just unitarity equation. S dagger is 1 when written in terms of t. Then one side is t dagger. Now if you put states on both sides, so they relates different loop numbers. So if you change this number arbitrarily, you might not get unitary result. If you change the GC arbitrarily.
Yes, if you change the GC arbitrarily. However, there's another thing, okay, and the other thing is that we haven't carefully looked at the normalization of our vertex operators. Our vertex operators should be, we've argued, should be C times V. But for unitarity, we need to know the number. And that normalization may also have some factor of GC. In fact, as you know, field redefinitions change that normalization in field theory. Okay, so it's a serious question. Okay, all of these issues we will deal with in fact, we will fix using the principle of unitarity. But wait, let me, so what I was trying to say was that, look, because in quantum field theory you've got this, because we're dealing with the kind of things that we don't normally deal with in quantum field theory, we have to multiply a determinant. There's some determinant times correlation function that gives us a string scattering amplitude. Like, do you remember we dealt with the zero modes? But in addition to the zero modes, there were some determinants left over. Let's say from the BC ghosts. Then what we will get in the matter sector is some correlation functions times the matter sector partition function, which in the end is some other determinant. Okay, so there will be some determinants left over. There will be a determinant on S2, a determinant on the torus, a determinant on the genus 2 surface, and that itself will depend on which manifold you're on. Okay? It will turn out that these determinants also have the following property. Okay? That they also behave with genus in a relatively simple way. Okay? So it's the product of these GCs with the determinants that really weight one loop with respect to two loops. So this GC is a rather formal thing because the determinants are a rather formal object. It's infinite. It's regulation dependent and so on. But it's the product of that which you'll see when we will regulate and use, basically using unitarity. And that quantity will play the role of the coupling constant of string theory. Okay?
You already have an alpha prime.
Alpha prime is not a coupling constant in string theory. Alpha prime is just a length scale for flat space string theory. And in flat space, it's really nothing. It can be changed by choice of units. Okay? Alpha prime becomes important if we're working on a manifold which has some curvature in it. Then you've got a dimensionless quantity, namely curvature and units of alpha prime. Okay? So talking about manifolds that are not flat space, we will come to. But at this point, alpha prime is nothing. Choice of units. Okay? So I just wanted to say this, and then now we'll move on. That string theory also has an effective coupling constant as associated thing. This quantity, the effective coupling constant has a name. It's called the Dilaton. And you will see, as we go on in our studies, you will see that it is associated. It is effectively associated with the expectation value of one of the fields that appears in string theory. Namely, the field that appears at the massless sector, the scalar field. I don't know if you remember, but in the bosonic string in the scalar sector, in the massless sector, we had a scalar, a symmetric tensor, and an anti-symmetric, traceless symmetric tensor, and an anti. The scalar is the dilaton, and that the expectation value of that dilaton is closely related to the is equal to the effective, the final effective coupling constant in this theory. We'll see many of these things as we proceed, but for now, I think we'll just move.
Was corresponding to a state.
Yes.
And then you want to calculate this 1 point function.
Yes.
So roughly, how do you go about it at least? You use some state operator map to find the operator that you want?
What we'll do is to show that shifting this dilaton is equivalent to shifting this alpha. So we will have to see how to formulate string theory on a background with some varying metric and Dilaton field. And then we will see that if you do that, then changing the Dilaton can be compensated by changing this alpha. Okay, that's roughly how we'll do it. Okay, but now we want to just proceed, and if everyone agrees, we'll just go on. We will just now continue. We will move on to studying the superstring. Okay, we had to take a call one way or the other. Let's do it. We'll try to do it fast, and so that we can come back to using all this stuff. We'll continue at least part of next semester. I think that's the only way to get through the subject. We'll do it. Fine. Okay. So now we're going to retreat back for a moment, back from our string scattering stuff to once again to the study of the string worldsheet. Okay, and in fact, for a while we'll retreat to some studying some conformal field theory. Okay, the first thing we have to do is to study the theory of a free fermion. Study the theory of a free fermion of a free massless fermion in one in 1 + 1 dimensions. We briefly went through the Lagrangian description of this in one class, but I'll quickly remind you so that we can proceed with familiarity. I'm going to write down the Dirac's equation in 1 + 1 dimensions and show you how simple it is. Okay, so Dirac's equation in 1 + 1 dimensions. What?
There is this Gaussianization in 2 dimensions.
Yes.
So why do you want to consider fermions?
Well, we want to consider fermions because
So sorry for my bad question.
no, it's not a bad question. We want to consider fermions because we're going to start, from logic, right? Logic will lead us to a theory with fermions, and then you can do any mathematical manipulation you want with it.
Okay.
Yeah. So when we try to generalize the string scattering amplitude, we will be led to a theory with Worldsheet fermions. So we have to get familiar with that theory. Okay. So consider first, just in flat space, the theory of Dirac fermions. Okay. So we have d to psi bar gamma del slash. Okay. Now, in order to completely explicate this, first we work in Lorentzian space and then we analytically continue. In order to explicate this Lagrangian, it's useful to use a particular choice of gamma matrices. It's useful to use sigma 0 is equal to I sigma 2, so that our gamma matrices will always be real, will be completely real, because sigma 2 is the only imaginary sigma matrix, and sigma 1 is equal to sigma 1, let's say. Okay, so I should say gamma 0 is gamma 1 is sigma 1. Okay, and then with this we just write this out. Okay. So this was integral d2 sigma psi dagger gamma 0 del 0 plus gamma 1 del 1 psi. This was the Lagrangian. Okay, so that's integral d2 sigma psi dagger. Now gamma 0 squares to -1. So that's minus right. So that's minus and del 0 plus gamma 0 gamma 1 minus I.
You do 2, 1, and then there's an I in the wrong place.
Yeah.
Sorry, plus.
So it's sigma 3.
Let's see. So 2, 1 gives minus I sigma 3, but there was an I here. So that's plus I, so that's plus sigma 3, right? Okay. And now we just open this out. Okay. We'll write psi, which was a 2 column, as psi plus, psi minus. Okay. So this becomes d2 sigma. Now this quantity is what? It is minus del 0 plus del 1 minus del 1. Psi dagger. Now in this dimension it's consistent to choose our spinors to be real. In fact, it's manifest that it is because we've chosen all our gamma matrices to be real. Okay, and we will choose these to be real, and yeah, and proceed. So this is d2 sigma psi plus del I think we call is this what we call del plus or del minus? Anyway, let's call it del minus for these purposes. This is del plus, then I'll call this del minus.
It's minus.
It's minus?
Yeah. The sign, relative sign, that's all.
Either
put a minus.
It's a matter of,
Fine.
it's a matter of convention. Yeah. Psi plus. If you insist on calling it del plus, I'll change these to psi minuses. Okay. Okay. Plus psi minus del plus psi minus. Okay. Now, as you know, once we do the analytic continuation to Euclidean space.
Why do you use that dimension you can impose this reality condition?
Well, just in saying that psi plus star was psi plus.
Oh, star, dagger, star. Okay, sorry. Forgot.
Yeah, but if I didn't impose it, I would get, these instead of being real, would be complex, would be too real.
Yes.
But just we're dealing with the minimal theory, so.
Yes.
Saying that the psi plus and minus are living in R2?
Psi plus and minus, well, at the moment in R11, but now we analytically continue.
Yeah.
Okay, so this becomes d2z psi plus del minus psi plus plus psi minus del, psi, let's call it z, del z bar psi z. And now psi z we'll just call psi, okay. And psi z bar we'll call psi bar. So psi bar del z psi bar. Okay. So so this here was our is our action, and in fact the action we're going to choose with the normalization to be exactly the normalization we chose for the BC system. You see, it's the same action as the BC system, as we commented once before in class. If you replace psi z, oh no, it's not. This is not. Sorry. If I had made this complex, if I had made it psi bar del z, psi. Suppose I had done this for a moment. Then psi star being B and psi being C would have exactly given us the BC system. So complex fermion is like the BC system, but at the moment we've got a real fermion, so let's choose our conventions. I'll choose the numbers behind the action. 1 by 2 pi S is equal to 1 by 2 pi S is equal to 1 by 2 pi d2z psi del z bar psi plus psi bar del z psi bar. I'll just make sure that the conventions match. Oh, 1 by 4 pi, sorry. Okay. Okay. So, fine. Now we're going to do the kind of manipulations we did before very, very quickly, because it's basically the same manipulation as in the BC system. But let's very quickly do it. What I want to do is to find the Green's function. What I want to do is to find the 2-point function for psi with psi. Clearly, psi and psi tilde are decoupled from each other. One is holomorphic, the other one is anti-holomorphic. Clearly, they decouple from each other. So let's focus on the psi. Okay. So as we look at is 1 by 4 pi d2z psi del z bar psi. And we're computing e to the power minus 1 by 4 pi integral psi del z bar psi. And I suppose we're using Polchinski's convention of, that was why he has a 4 pi. Yeah. We have a 1 by 2 pi if we have d2 sigma. And this is what he calls d2z. Okay. So d2z is equal to 2 d2 sigma. Okay. Now what we do is, as usual, we put a psi in here at z prime. And we have a d psi, and we do d by d psi of z. Okay. And now we do it keeping our wits about us. Okay. So the first term we get is delta of z minus z prime when this hits this. Then we get a minus because we go through here. And we get a minus because we vary the action. Then we get a 1 by 4 pi. Then we vary the first guy. Okay, so we will get psi of z prime del z bar psi of z. And then we get minus when we go through, or well, both terms will be the same, because for the second guy we integrate by paths. That gives a minus, and then we take it through. That gives another minus. So just make it 1 by 2 pi. Okay. Now let's start with a 1 by 2 pi and write it as d2 sigma. So we know what we're talking about. So this is a 1 by pi. Then this is a usual delta function, the standard flat space delta function. Okay. And then we have to solve this equation, and I'm claiming the solution is 1 by z. So claim psi of z prime is equal to 1 by z. Okay, we agonized through the factors of pi last time. It's the same calculation. I'll leave that to you. Okay, so we don't have to go through it again. Okay, we had long discussions on whether this function equation uniquely determined the function and so on. Okay, it's the same, all the same. So fine. So we've got this 2-point function. So the theory has basically the same 2-point function as BCCFT, except there isn't a B and a C. It's just one field. It's psi. Okay. Now the next question is, what is the stress tensor? Okay. So I'll write down a stress tensor and then we'll check that it works. Minus half psi del psi. Okay, claim T is equal to minus half psi del psi is the stress tensor for this thing. Okay, let's very quickly check that. Okay, so what we want to do is look at 1/4 of psi del psi at z with psi del psi at 0. Okay, let's check firstly the maximally contracted term. One contraction is this with this and this with this. In this there are no signs. Okay, in this there are no signs. This is, let's call it a z prime. This one has 1 by z minus z prime, but it's derivative. So that's minus 1 by z minus z prime square. And this one has 1 by z minus z prime, but it's derivative with a plus. So that has 1 by z minus z prime square, which already looks a little odd. Right. What and a quarter. What I don't like is the sign. Oh wait, but this is just one of the terms. Let's do the other term and see. Yeah, but it's just going to add up. I don't like the sign. Something's a bit wrong with this. Oh, well, no. There's one more contraction. There's this with this. Okay, let's do it all and then we'll obsess, because this has additional derivatives, additional factors. So let's do it. Okay, now let's do this with this. Firstly, there's a minus sign, okay, because you have to take this through to do that. So then you get a minus 1 by z minus z prime, and then this with this. That gives 1 by z minus z prime, and then two derivatives, but one on one side, one on the other, so no sign. Okay? Overall?
With that minus.
Because
There will be minus sign coming from only one of them. Overall plus.
you have a minus from commuting, and then the two derivatives.
Yeah. You're right. Overall, there's overall a plus. There's a minus from derivatives, and from the derivatives we get a minus sign, because both derivatives otherwise have given us a minus, but one is a wrong sign derivative. One is a derivative with respect to 2. So there are 4 minuses. There's a minus from the commutation. There's 2 minuses from the derivatives, and there's 1 minus because we're taking a derivative for the second argument. Okay, so that's a plus. And now the factors. First derivative gives us a 2. No, first derivative gives us a 1, and the second derivative gives us a 2. So plus 2. Now, what? To the power of 4. Thank you. So now we get 1/4 over z minus z prime, the whole thing to the 4. with a plus. And so we see that C is equal to half. What? No, there's 2 and there's minus 1. So 2 minus 1. Okay, great. Now, just as a sanity check, let's get the other contractions. So if we get, okay, it's a bit painful, but let's just do it. We can contract this with this. So we get 1 by z minus z prime square with a minus psi of z del psi of 0. Everything with the 1/4. Plus contracting this with this. So we get plus psi of 0, no, psi del psi of z, psi of 0 of z prime, and then this contraction gave us minus of what we got before. So z minus z prime, the whole thing square. Okay, now then we had this with this. So minus 1 by z minus z prime, and now we don't need to keep track of what is where. So times del psi of z, the whole thing square, which is 0. Of z prime, the whole thing square, which is 0. Okay, and then there was this with this. Okay, so that will give us, okay, so there's a minus sign. Minus sign because I took it through. Then I get psi of z, psi of 0, z, psi of z prime. And then the contraction gives 1 by z minus z prime, then minus into minus into minus. So plus and 2 z minus z prime cube. Yeah. All okay? What? Okay, this guy's gone. This guy is 1 by 4 into minus, well, the first term is psi of z prime del psi of z prime by z minus z prime. What?
We get the same thing from the next one, just with different swaps. So
right. We'll get the same thing from the next one because we reverse the order. Thank you. Minus 2. Right. Okay. And then there's the term that comes from here, which was the Taylor expansion. Okay. So the term that comes from here, that was the Taylor expansion, was plus. It's going to be a del psi, which is 0, right? So the first order term is just 0. Okay. Then there's the term that comes from here. What? No, not the Taylor expansion. Right, because here we're supposed to expand z around z prime. Okay, so that'll give us del square psi. Okay, so that's plus del square psi of z prime, psi of z prime, of z minus z prime. Okay, and now we're supposed to also Taylor expand this.
first term is gone.
This is some sign issue.
You can't have psi, so that's.
Oh, no, this is okay. Yeah, right. So the first term is gone, exactly. The second term is 2 del psi of z prime psi of z prime by z minus z prime the whole thing square. Yeah, and del psi, so good. And last term is the 2 goes, so del square psi of z prime by z minus z prime. Okay? And then we put this together. So this plus this, because the order is flipped, is 4. And so we get minus, it's 2 into minus half psi del psi. But that was the stress tensor itself over z minus z prime the whole thing square. And these two terms together are plus del of minus half psi del psi by z minus z prime the whole thing squared. Because when you act with this del, the first term del psi is 0. The cross term is psi del square psi. And there are 2 such terms that cancels the 1/4 to give you the half. What? This is the translation. Okay. So we've checked that this is a legitimate stress tensor for this theory. And it is the stress tensor if you take this theory, couple it to the metric, vary with respect to the metric. You know, if you worked out what the stress tensor of the Dirac Lagrangian is, you will find that it's the stress tensor. I won't go through that exercise, but it's an but it is. Okay, very good. Okay. Now, yeah.
This psi is function of z only or z and z bar both?
Well, off shell, of course, is function of both. But the equation of motion tells you that del z bar psi is 0. Right? In fact, this was that same equation of motion. This is the contact term in that equation of motion. So it's a holomorphic function. Okay? Now, one of the main things that we want to so this is the theory of the free fermion. Okay. Now, what I want to do is to show you that you can take this free fermion and put it together with a boson to make a superfield. Okay. And this is the structure we're heading towards. Okay, so let me maybe give you a minute about what we're trying to do. What we did so far was to work with what's called the bosonic string. You saw we got the structure of a supersymmetric. We got the structure of a conformal field theory on the worldsheet. In order to improve this, what we're going to do is just supersymmetrize this construction, but on the worldsheet. Okay? You might ask why. Okay, so maybe I should immediately tell you why. Firstly, why should we have fermions on the worldsheet? Look, clearly we want a theory that is capable of putting fermions in space-time. Right? Our world is full of fermions. If we want string theory to be anything like our world, we want fermions. So clearly we want, the bosonic string, by the way, had no obvious fermions. It's a bit, then it turns out there are solitons in the bosonic string that are fermionic. Mm-hmm.
Is it this are you calling D-branes as solitons?
Yes. In fact, there are certain, if you have a D-brane, another D-brane, and an open string stretching between them, you can make some of these open strings fermionic. Okay? It's an interesting thing. But it doesn't matter. Naively at least, in perturbation theory, there was no space for any fermions. Right? One of the first things we want to do is to allow for having fermions in spacetime. Now, if we can do that and also cure this tachyon problem, then we would be very happy. Okay? we're trying to head towards that. Now, I want to get fermions in space-time, and I'm claiming that putting fermions on the Worldsheet will help us do that. That might seem sort of reasonable because fermions are fermions or whatever, but it's not so clear. And you might ask, can you give a clear argument that fermions on the Worldsheet will give you fermions in space-time? Let me give you the argument. Let's go back to Lorentzian space for a moment. Okay? In Lorentzian space, we had, if you remember, psi minus, del plus psi minus. And let's take this Lagrangian. Now, let's put back the fact that we're going to deal with psi's that are many, just like we dealt with x's that are many. What I'm going to say now will give you motivation for the following claim. We should deal with as many psi's as x's. That is, I'm going to put a vector, space-time vector index on the size. Exactly. Just like there were as many x mu's as there were dimensions in space-time, I'm going to put as many fermionic directions as there are dimensions in space-time. Why? This is going to be an obvious bit of motivation. Let's take this and canonically quantize it. When you take it and canonically quantize it, we'll get a lot of oscillators. That's not what's of interest to me at the moment. What's interest to me is at the 0 modes. So, if I have this theory and I look at configurations that are just translationally invariant, then del plus becomes del 0. So we look at just the translationally invariant modes, modes that don't depend on the sigma coordinate on the cylinder. Del plus is del 0 for such modes. And this thing here is psi minus mu, del 0, psi minus mu. What is the quantization of this structure? This is like coordinate and momentum, but anti-commutation. We'll do this properly at some point, but you all know, right? The psi mu, psi nu. What? Clifford algebra, exactly. This will be quantized by implementing this kind of anti-commutation relation, and therefore will give you the quantization will be that psi mu will become gamma mu. It's like having
it's psi dot.
Right? Psi dot, yes, psi dot, exactly. But exactly, psi dot. But the answer to that quantization is a finite dimensional Hilbert space. What is that finite dimensional Hilbert space? It's the space of d-dimensional spinors. And the action of psi on that space is the action of gamma of the quantization gives you that psi acts as the operator gamma mu. In particular, now, what? Of those gammas, exactly. This is the d-dimensional generalization of those gammas. Now, what we can look at the generator of Lorentz invariance on this space. As usual, it will be I by 4 gamma mu commutator gamma nu. The usual story. And this acts on what space? On the space of spinors. This quantization will give you a chiral spinor, depending on how many, whether the dimensions are odd or even.
Lorentz transformation is space-time Lorentz.
Space-time Lorentz transformation. Okay, we'll give you a chiral spinor plus an anti-chiral spinor if we're working in d dimensions. And all modes will transform. The modes in the zero mode Hilbert space will transform like a spinor and an anti-spinor. So now let's look at our wave functions when we finally quantize everything. Chiral spinor and anti-chiral spinor. You don't know about spinors in arbitrary dimensions. There's an appendix in Polchinski volume 2. Please read that. It will take us too far away to start talking about such things. If you really need to, we can do it. Okay? But what's important? The important thing is that now if you look at wave functions on the worldsheet. So what's the Hilbert space on the worldsheet? Hilbert space will be, we're going to head towards a theory with both the bosons and the fermions. There will be harmonic oscillators from the bosons and harmonic oscillators from the fermions. That's clear, right? In addition, there's a zero mode of the fermions, there's the bosons, as before, and the zero mode of the fermions. The full state in the Hilbert space is a product state in each of these sectors. As before, the harmonic oscillators will just give us some level number, which will fix some Marshall condition. But in addition, the theory will be a wave function on the bosonic zero mode sector and the fermionic zero mode sector. To specify which state you're in the bosonic zero mode sector, you specify a moment. You specify which state you're in the fermionic zero mode sector, you specify a spinor. Not a gamma, a spinor. Gammas are the operators. We want the Hilbert space. Right? And then, how do states transform under Lorentz transformations? They transform like spinors transform. So it's clear that in any sector that has fermionic zero modes, all the states in the Hilbert space will transform under Lorentz transformations like spinors, and therefore will all be fermions. You see, what is according to the spin statistics theorem, in space-time, every fermion transforms in a spin half representation. Every boson transforms in an integral representation. We just said that in all our modes will transform in spinorial representations.
Can we tensor different spinors and get other stuff, or are we one
Very good.
fixed?
No, very good. We're coming to exactly your question. Okay. At the moment, it sounds like all our modes will be in spinor representations, and therefore will be fermions. However, I've only dealt with one half of the string. There's the second half, the psi bar, that has its own spinors. And if you tensor spinors with spinors, you get non-spinorial representations. Okay, so naively we've not succeeded, but there's room for it, right? Now, let's think a little more. Why did we get the zero modes? Because there was a sector in our fermions with zero momentum. What? Shift symmetry. But suppose we did the thing that Indranil was talking about earlier in this class. We looked at, you see, when we study fermions, it's not enough to say what manifold you're on, you have to also specify the spin structure. Suppose we work in spin structure in which the fermion is antiperiodic as you go down the circle. Then there's no zero mode. In such a sector, all states will be bosonic. Now, if we're going to allow,
It is a constant and it cannot change itself easily.
yeah, a constant automatically has even spin structure. Can only survive if you have even spin structure.
Automatically periodic.
Periodic, exactly. So, if we're going to allow states which are in one spin structure on the left and the other spin structure on the right, those will be fermions. States which have the same spin structure on left and right, whether periodic or anti-periodic, will be bosons. Now, can we put all these ingredients together in a consistent way? That's the subject of the next few lectures. But you see there's room for it. There's room for getting fermions once you, in space-time, once you have fermions on the worldsheet. Is this clear?
There's something missing. So the initial action, the fields on this worldsheet had they're really coordinates of embedding space.
Yes.
What should we think about
Yeah.
this as?
Yeah. Now, you know, hard to say. What they are not is the theta directions of superspace in space-time, because those would be spinors in space-time, and these are vectors in space-time. It's very important that we're going to get spinors in space-time by quantizing the zero modes of vectors on space-time. That's this Clifford algebra. Okay, that's going to be our structure. Okay, we're not going to start with spinors in space-time, which then could have had the interpretation of as fermionic coordinates in target space.
Yeah, the thing that even in bosonic string, why did you need to have this mu index at all?
That was very clear, because what we wanted to do was to study maps of a two-dimensional world surface.
The motivation part.
Hmm?
It came from this action which was an area, and then that gave us naturally mu.
Yes.
But I am saying once we have got this thing, now can we not forget that? And this is like various representations you can put.
Well, you wanted a Lorentz invariant. Zero modes of that will be labeled by momentum. If you want to describe motion in flat space.
If I want to describe motion in flat space, then I can have vectors like the ones that we have. In space-time, I can have vectors. In space-time, this is the space-time vector.
This
and bosonic string was also space-time vector.
Yes, was a space-time vector. Yes.
I can mix space-time Lorentz invariant quantities by not talking about vectors, some other things in space-time.
But the zero modes of whatever you do will be associated with the momentum. And momentum in flat space is associated with e to the power p dot x, where x is a direction, a coordinate. Yes. Right? So if you want ordinary momentum modes, you better start with coordinates.
We're going to map into d dimensions, and we're going to have, let's say, d bosonic maps that will be your embedding maps, right? And then, for some reason, carried along to the right is an additional d fermionic map.
Yes.
Right? And you're saying that the case is not that in our target space we're saying that's a supermanifold.
No, that's not the case.
This
Yes.
is not what we're doing.
That's not the case in the formalism I'm going to present to you. Okay.
Okay.
I should make one clarification. There are three inequivalent presentations of the superstring. These are called the NSR formalism, which in some ways is the most logically elegant, and that's what I'm going to present here. Okay? But has the defect of not having a clean answer to your question along the lines that you're enunciating. However, as you will see, 10 dimensions will effectively become, 26 dimensions now will effectively become 10. Okay? And up to gauge invariance, 10 will become 8.
I guess I'm also confused about that, just because I know I have to cancel the Weil anomaly.
Yes.
I'm just counting dimensions, and I know what the factor is going to come from the fermionic direction, and I'm just not seeing how they're going to cancel on 10 dimensions.
Okay, that's also coming. It's not going to cancel because you're assuming that the ghost structure has not changed. We'll have
No, but there's going to be bosonic ghosts now. Right?
what?
There's going to be bosonic ghosts.
Exactly. So the minus 26 will get a plus something. Will get an additional plus something, which will make it plus 50. The net will become minus 15.
My target is wrong.
Right. Right. Okay. I was just going to come to that point. So, go on.
Is it going to be more than just for symmetry? It will have more symmetries. More gauge symmetry. More gauge symmetry.
Exactly. This is the point I'm coming to next.
Because otherwise, you're
Ex-
taking him.
Ex-
Sorry.
No, exactly. We'll have more gauge invariance. So I'm next coming to. But what was the last point we were discussing? Does that?
Your comment was that you took vector representations because momentum was a vector.
Yes.
That's the clear motivation.
Yes. And so all we are going to do is supersymmetrize the worldsheet. Right? Take the formalism we had from the bosonic, and on the worldsheet supersymmetrize it. Okay, that's
So the worldsheet will have two-dimensional right? It'll have a tangent space that will have two bosonic and two fermionic directions.
there will be fermions that live.
And there's my worldsheet right now is coordinates sigma, whatever sigma 1, sigma 2.
Yes.
And now we're going to take sort of
Sigma and theta. Yes.
A theta 1 and a theta 2.
Yes.
Right. Okay.
Yes. Exactly.
But you want to preserve the conformal symmetry, therefore probably you use superconformal.
Exactly. Exactly. So now, but let's see the motivation for that. Okay, but that will of course happen, but there's more. Remember, we took motion in d-dimensional space, but in the end we wanted to get only d-2 physical excitations. Okay, this made sense from many points of view. Okay, now it had better be that something similar happens with the fermions, because otherwise we'll have ghosts. Because eta mu nu in the commutation relations. So it had better be that the fermionic oscillators also aren't d-dimensional fermionic oscillators, but d-2 dimensional fermionic oscillators. However,
One dimension you surely want to get rid of because beta has a minus. You want to get rid of one more.
yeah, right. Usually these things happen in pairs. That, right. For instance, if you think of, there'll be one got rid of because of the gauge and one because of the constraint. Okay. Now, the way we're going to try to do, how are we going to do that? See, we've used up all our old symmetry. We just had conformal invariance. We've used it up by getting rid of the fermionic oscillators. No, so the bosonic oscillators. All the fermionic oscillators will still be left. So what we need is a new gauge. You see, effectively what we did is gauge the theory by the conformal group. You see what I mean now, right? Because things that were conformal descendants of a primary were pure gauge. Okay? So we're going to need to do something similar with a fermionic group. Okay? So as to be able to get rid of the additional fermionic oscillators. So what we're going to do, of course, the theory will have superconformal invariance, and we will gauge the theory with superconformal invariance. That's the way it's going to work. That's how we'll be able to throw away the extra fermionic degrees freedom. Okay? So for that, we better have an enhanced symmetry algebra.
You are going to gauge the supersymmetry as well.
The full superconformal group. I mean, our physical states will be primary operators under the notion of primarity of superconformal group. Okay? In order to be able to do this, we need something like a superconformal algebra. We need an enhanced fermionic symmetry. And the simplest way, as you guys have guessed and we have said many times,
Local supersymmetries will be gauged.
local supersymmetries. I mean, these conformal kind of,
Independent supersymmetries.
these conformal supersymmetries. So it's not going to be, okay, yeah, there would be a Polyakov, there will be a gravity version of this action in which we would be gauging supergravity.
Yes, that, okay.
This, and in a while invariant way because it's 2 dimensions. This is right. But we're going to start our presentation directly in a gauge fixed form, as you will see. We'll build it up. Okay? In that form, we will effectively have the superconformal generators as a constraint algebra. Just like we had the conformal generators as a constraint algebra for the bosonic string, we're going to have more constraints to get rid of the bad fermionic oscillators. This gives you motivation for, the motivation for introducing fermions is to get fermions in space-time. But the motivation for doing so in a highly symmetric way is so that we have a symmetry algebra we can gauge. We can impose as a constraint. Okay? It's clear that one way of doing it is just to find supersymmetry. It's just to use supersymmetry on the worldsheet and maintain supersymmetry also at the level of the gauge algebra, of the constraint algebra. That will automatically do what we want. Okay?
You had bosonic strings and you have some conformal symmetry.
Correct.
They are fine.
Correct.
Now you have some fermions and you wanted some principle to get rid of some of the degrees of freedom.
Right.
And then
And it's very important that the conformal invariance in the end was not just a global symmetry of the theory, it was gauged, right?
if it is gauged, then the only notion in which we can enlarge it is superconformal. This is why super came. I am trying to use super.
Yeah, I'm trying to do it in a way so that I get a higher gauge algebra, a higher constraint algebra, to get rid of the bad fermionic oscillators. Very simple way is to supersymmetrize everything, including the constraint algebra. Then you will be throwing away more stuff.
This, when we did the bosonic case, right, we said that when you're embedding it into the 26-dimensional space, two of the directions are diffeomorphisms.
Correct.
Now we're embedding it into whatever dimensional space. Two of the bosonic directions are diffeomorphisms, and two of the super directions are also diffeomorphisms. And all of those can't be a physical degree of freedom. So it's really
Exactly.
Okay.
Exactly. We want some principle that will get rid of two of these,
Right.
and we just do it in a supersymmetric way on the worldsheet.
Can we just do the same thing again? Faddeev, Popov, get the ghost.
We will.
Smatter?
Oh, we could.
Right.
All we'd have to do is this. You know, in Polyakov form, our action was simply supergravity in two. It was simply gravity in 2 dimensions coupled to a scalar field. Okay. Now, if we just write down an action for supergravity in 2 dimensions, coupled to a superfield, we'll get what we get. Just that. And then gauge fixing that. Okay. The jump is to do the supergravity in 2 dimensions. You may question that. Of course, I'm giving you, a way of thinking that makes it sound, there's some story. When it was first done in the 1970s, this is where supersymmetry was invented, right? From that there was an existing supersymmetry structure that people just wanted a higher constraint algebra. And this is how they invented supersymmetry. The first supersymmetric theory was written down on the worldsheet of the string. So, it's a bit anti-historical the way I'm presenting it. But so they actually invented supersymmetry because they wanted this. They wanted a new constraint algebra that would get rid of the fermions. That led to supersymmetry. Okay? Fine. So this is where we're going. Okay. Great. So now
I don't understand why, like when we were dealing with bosonic strings, we just look at just the boson. So why can't we do the same with the fermions? Like just look at the fermions. Why can't we do the same?
well, see, suppose we had just the fermions, then we won't have any momentum. There's no space in which things will be propagating. The x's were the coordinates in which things propagated. So we want fermions moving in some space. So the x's built up that space. And then you have a little additional structure. You see, think non-relativistically. What's the difference between a fermion and a boson? Not much, right? A boson is a Schrodinger wave function. A fermion is a column of Schrodinger wave functions. But Schrodinger wave functions of x. So we suddenly want that x for it to be this was just giving us the column, as you've seen. But we also want the x. Otherwise, we'd be living on a point.
You can't go very far in the super direction.
That's right.
You can take 3 steps and you're 0.
Right. Right. Okay. I'm going to have to go in like 2 minutes. Yeah. What was the next thing I was planning to do when I started this deviation? I was planning to introduce superspace. Maybe that should Let's wait. Let's keep that for next time. I have to pick up my son in 20 minutes and it'll be late. Okay, so let's keep that for next time. Okay, so okay, I'm very sorry, but next week, which is Diwali week, I'm out of town. Okay, so we'll have to resume class the following week.
Can you give us some reference for if there's some prerequisite required for next classes?
Okay, good. Something, if you guys don't know, is go through the appendix in Pulchinski volume 2 on spinors and supersymmetries in various dimensions. This is very well written, very elegantly done, and that will help us a lot. If you just know the notation, that would help us a lot. Our discussion of supersymmetry on the worldsheet will be self-contained. In fact, the easiest way to learn about supersymmetry in general is to first learn about it in low dimensions. Simplest place is supersymmetric quantum mechanics. If you want to learn about supersymmetry, which is a good thing to do independent, read these beautiful papers by Witten in the 1980s, these nuclear physics papers, constraints on supersymmetry breaking and so on. Read those. Those are very useful. I mean, and they're classic physics. So independent of the course, yeah, if you read those, you're in good shape.
Just ignorant, rooted terminology question. This is called n equals what supersymmetry? Like I've seen this phrase n equals, I just don't know what it is.
Yeah. The supersymmetry we will be using will be called 1, 1, because there will be one supercharge on the left and one on the right. And it is basically, I suppose you can have 1, 0. We will also, in the heterotic string, we will deal with 1, 0 supersymmetry. But it's so little supersymmetry. The general rule is this, that if on any one side you have less than 2 supersymmetries, supersymmetry allows you to organize your action and so on, but it doesn't give you much dynamical power.
What was the statement? When does not give much power?
When you have, roughly the statement is when you have less than 4 supercharges, you don't get dynamical power. But that statement is a bit crude. The accurate statement is that if you've got a chirality, on any one chiral side, if you have 2 supercharges, you get power. What do I mean by power? I mean the following. Much of the power of supersymmetry comes from holomorphicity. There are terms in the action. If you've got a theta, there are terms in the action that have to be holomorphic functions of some supervariables. And this happens when you've got 2 or more. Okay. Now that's very important for the following reason. You see, suppose I've got a field of charge phi, charge 1, okay, and I require that my action is neutral. Without supersymmetry, this doesn't constrain things much. It tells you everything is a function of phi bar. But with enough supersymmetry, phi in certain terms in the action, you are allowed to put a phi, but not a phi bar. There's some holomorphicity in field space. One of them is called chiral multiplet, the other is an anti-chiral multiplet. Certain terms you can have chiral multiplet, but no anti-chiral. Okay? Now that immediately tells you that you've got a lot of power, because if you've got only one charge field,
Many times you can't write down.
then in terms of this form, you can't write any terms. So that tells you there are certain terms in the Lagrangian that you have a great deal of control over. It gives you more constraints on dynamics. Okay? So it allows you to make some exact statements about dynamics. So the general rule is when you've got 4 supercharges in general, or 2 or more on one side, really, that's a more accurate statement, you get this kind of non-trivial dynamical control. One supercharge like we have gives us very little dynamical control, but allows us to organize our theory. That will be enough for us because we are dealing with a free theory. We don't need the dynamical control. free theories even we can solve, right? Okay, right. So we will be dealing with the simplest kind of supersymmetry, and so in some sense the most boring. But it's so simple that everything will be completely explicit. Our superspace will be completely explicit. All our manipulations will be trivial manipulations. You'll see. And it's a great place to learn about supersymmetry. So you shouldn't feel that in order to understand the next few lectures, you need to learn about supersymmetry. Quite the converse. In order to learn about it, supersymmetry comes to the next few lectures.